All right, today we are going to tackle one of the most powerful and maybe one of the most mysterious looking symbols in all of math and physics, the del operator. And I promise, by the end of this, you're going to know exactly what it does and why it is so incredibly important.
So you've probably seen this upside-down triangle thing before, right? Maybe in a physics class or some science documentary. But here's the big secret. That's not just a shape. It's a command. Seriously, it's a set of instructions just waiting for us to tell it what to do. And today, yeah, we're going to learn how to use it.
Okay, first things first. Let's get properly introduced to the operator itself, del.
Now, the official definition calls it a vector operator describing differentiation with respect to multiple directions. Okay, that is a mouthful, I get it, but the key idea is actually pretty simple. It's all about measuring change, but not just forwards and backwards. It measures change in all directions at the same time.
You know, the best way to wrap your head around del is to think of it like an engine without a car, or an instruction manual for a gadget you don't have yet. By itself, it doesn't really do anything. It's just a list of actions, like measure the change this way, measure the change that way, just waiting for something to actually apply those actions to.
So what does del act on? What's it waiting for? Well, the answer is something called a scalar field, and this is where we get to start mapping the world around us.
Don't let the name scalar field throw you off. The idea is beautifully simple. Just picture a map, any map. Now imagine that at every single point on that map, I mean every point, there's a number, a single value attached to it. That's it. That's a scalar field. It's just a space that's filled with information.
And this comparison just nails the difference. A scalar? That's just one number. It's like saying, hey, the temperature right here is 25 degrees. But a scalar field, that's the whole picture. It's the complete map showing you the temperature at every single point in the entire room. Over by the cold window, above the warm radiator, everywhere.
Okay, to really make this stick, let's use an analogy we're going to come back to. A mountain landscape. Think of a topographic map. Every single coordinate on that map has exactly one value tied to it, right? It's altitude. That altitude map is a perfect real-world example of a scalar field. So let's keep this mountain in our minds.
All right, it is time to put the pieces together. We've got our operator, del. We've got our map, the scalar field. And when we apply that operator to our map, we get something incredibly useful, the gradient. Or, as I like to call it, the uphill arrow.
So here's how it plays out. We take our operator, that little del symbol, we tell it to act on our scalar field, which we can just call f for function. That's our mountain map of altitudes. And the result, what we create, is written as del f. That is the gradient. See? We've just given our instruction manual something to actually work on.
And this right here is the million-dollar question. So what? We've stuck some symbols together. What new information have we actually created? What does this gradient thing really tell us about our mountain? Here it is. This is the big reveal. The gradient is a vector, which just means it has a direction and a length. And it always points in the direction of the greatest, fastest increase. It literally points you the steepest way up. Let's bring that right back to our mountain. Imagine you're standing anywhere on that landscape. The gradient is like an arrow that magically appears at your feet, pointing you in the exact direction of the steepest, most direct path up the mountain from right where you are. And if you move, that arrow instantly updates, always showing you the quickest way to gain altitude. It's your own personal, straight uphill detector. But it gets better. The gradient also tells you how steep that climb is. The length of that arrow, what we call its magnitude, tells you about the steepness. If you're on a nice gentle slope, the arrow's pretty short. But if you're on the side of a cliff, well, that arrow's going to be very, very long. So you get both direction and intensity.
So we have this uphill arrow. It's a neat concept for a virtual mountain for sure, but this idea is so much bigger than that. Let's dig into why the gradient actually matters so much in the real world.
The reason the gradient is such a game changer is because knowing the direction of steepest change is a critical piece of information. Because if you know the fastest way up, you also know the fastest way down. And being able to find that optimal path, uphill or downhill, is the key to solving a mind-boggling number of problems.
And the applications are, well, they're everywhere. In machine learning, AIs use what's called gradient descent. They literally walk down the steepest path to find and minimize their errors so they can learn. Weather forecasters use gradients to predict where the wind will blow.
Video games use the gradient to figure out how light should bounce off a surface to look realistic. It's just everywhere.
So, if there's one thing you take away from all this, let it be this. The gradient does something magical. It takes a scalar field, a static map of plain old numbers like altitude or temperature, and it transforms it into a vector field, a dynamic map of arrows, of directions. It gives a sense of flow and change to something that was completely static.
So we've totally mastered how to find the uphill direction. But that del operator, it's got more tricks up its sleeve. What if instead of steepness, we wanted to measure spin? Like, imagine our field was a swirling pool of water. How could we possibly measure the rotation at any given point? Well, that would require a different command. And that, my friends, is a story for another time.